We've ended the last video with this form for the Hamilton-Jacobi equation, and we've said that this form admits solutions for S in the following form. S is written down as a function of W, which is a function of vector Q, the position vector, minus alpha t, where alpha is a constant. And t is the time, right? Now what we're going to do is just like to plug in with this S right here in the above Hamilton-Jacobi equation and see what we're going to get. Doing this gives us the following. H as a function of Q, partial S, partial Q, the vector Q, close the brackets, plus partial S, partial T. As we can see here, partial S, partial T is nothing more than minus alpha, right? And that's all equals 0. 0. For a lot of systems, we'll have this Hamiltonian here representing the total energy. So that means when we take this alpha here to the opposite direction by the opposite sign, we're gonna get the following. H the function of Q minus partial S partial Q, the vector Q, and that's all equal to alpha, right? So because, like I've said, this H right here is gonna represent for a lot of systems the total energy. We just like can assume that this alpha here is nothing more than the total energy E, right? And that tells us that the final form of solution, that is S, will be as the following. W is a function of Q, the position, minus ET, right? This form actually is really important because it will be the starting point when we get to Schrödinger's work. And actually we're gonna get to this in a moment. Now, after we just like discuss the Jacobi equation and how to solve that, and the last form for this Hamilton-Jacobi equation, we just like solve it out in the last 2 moments. Now we've got all the tools we need to start talking about what Schrödinger exactly did back then in 1926 to be able to get the famous Schrödinger equation. That's what we're going to do right now. First of all, Schrödinger pictured this a simple system, like a system of particle moving in a conservative force field. And by conservative force field, I mean a force field which can be written down as the gradient of some potential function. And this potential function I'm gonna choose to be V as written down in the Cartesian coordinates. That is, it's a function of x and y and z. And let's picture this here to be the particle. So what Schrödinger is gonna do now? What do you think he's gonna do? After just like he pictured the system, he'll try to solve it, right? So he'll write down the Hamilton-Jacobi equation for this system, and let's see what we're gonna get. The Hamilton-Jacobi equation for this system, like we can see now that this is a particle moving in conservative force field, so that means the Hamiltonian H is nothing more than the total energy. Q partial S partial Q, that's nothing more than the total energy. So that means all we need to do is just like write down the total energy for this, then we plug in, we substitute HP with the corresponding partial S partial Q, right? So let's do this. The Hamiltonian for this system will be H as a function of P, right? And X, right? Let's see what we're gonna get. X, Y, and Z. P here, I mean the vector P, the momentum vector, the conjugate momentum. And that will equal to P squared, the vector P squared, right? And that means the dot product of this vector P here over 2m plus V, and that one is a function of X and Y and Z. So that was the form of the Hamiltonian, right? We just like need to write this down in the above form. So that means we have to take HP. First of all, we have to write down this dot here except to be able to make the substitution easily. 1 over 2m px squared plus py squared plus pz squared plus v as a function of x of y and z, right? Actually, I'm gonna continue in the next video. That was it for this video. Thanks for watching.